Very good afternoon, students. How are you all? Can you all able to hear my voice? Good afternoon, everyone. Good afternoon, Vaishnavi. Yes, good afternoon to all of you. Yeah, good afternoon, Sanika. Very good afternoon. So all of you can able to see the screen and I'm visible and audible, right? Yes. Okay, fine. Okay, sir. Good. So yesterday, the new chapter was started no, by Vivek sir. And I think you guys have gone through some of the introductory part of this B and F block elements lesson, and some general properties were discussed yesterday, right? Like ionization energy. So those kinds of things were discussed yesterday. So let me just recall, okay, once again, and then we will move on with one or two slides, and then we will move on to the new topics for today, okay? So coming to the D and F block elements lesson, D and F block elements, D block elements mainly, they are called as transition elements. Okay. So according to IUPAC, transition metals means the metals which have incompletely filled the subshell in their neutral state or in one of their ionic form. Okay, so yesterday a detailed explanation have been given to you by Sir for this. Okay, so they are called as transition elements. So all D block elements are not transition elements, but all transition elements are D block elements. Okay, so the exception is zinc group. So zinc group basically they are not regarded as the transition elements because they have completely filled the subshell in their neutral form as well as in their oxidized form. So they are not considered as the transition element. So all D block elements are not called as transition elements. Okay. So coming to the periodic table, we have four blocks: S block, P block, D block, and F block. And in this lesson, we are going to study about the center part of this periodic table, which is D block. So D block consists of how many rows? So there are four rows. D block consists of four rows, right? So from scandium to zinc, so they are called as 3D series, and from yttrium to cadmium, called as 4D series, from lanthanum to mercury, called as 5D series, and from actinium to copernicium, it is called as 6D series. So in this lesson, we will discuss about both D block and F block. So first we will be concentrating on D block, and then at last we will move on to F block. Got it? So all of you try to memorize the 3D series. So first of all, try to memorize the 3D series. Okay, so that is from scandium till zinc. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So at least you have to memorize the 3D series first. Got it? Have you all memorized? So yesterday this lesson was started, no? Has anyone memorized the 3D series? So Sakshi has memorized. Very good, Sakshi. Any other? So you should be able to tell. So without memorizing, without by hearting the 3D series, so some of the, not some of the, most of the general properties will become very difficult for you who did not memorize. Okay, so try to memorize the series. So because their electronic configurations are very important. The atomic number starts from 21 to 30 for scandium till zinc, right? So electronic configuration also will go in that way, like 3D1 4s2, 3D2 4s2, 3D3 4s2. So either you have to memorize the electronic configuration or you have to memorize the elements. So better go for memorizing the elements. So that will be very helpful for you. Got it? So yesterday some chromium and copper. So those two group elements have some exceptions for electronic configurations that have been discussed, I think. So am I right? So did sir discuss about the electronic configuration part? exception case for chromium and copper. Yes, yeah. So those things are very important. So try to memorize the 3D series first, and then I will tell you how to memorize the remaining things. Okay. So now let's move on to the new topics for today. So the learning objectives for today, they are the general properties. So yesterday some of the general properties were discussed, like atomic size and ionic radii and melting point and enthalpy of atomization. So those things were discussed yesterday, right? So today we are going to study about the oxidation state, standard electrode potential, and the stability and magnetic properties of these transition elements. Got it? So let's start with the oxidation state. So coming to the oxidation state, so we are going to study the oxidation state for 3D series. Okay. So if you look into the, if you observe the oxidation state for this 3D series, so except scandium and zinc, all other metals have variable oxidation states, right? So D block elements can exhibit variable oxidation state. So it is one of the very important property which we have to keep in mind about D block elements. Okay, so D block elements exhibit variable oxidation state. So the exceptions are scandium and zinc. So they cannot exhibit variable oxidation state. Variable oxidation state means different oxidation state, multiple oxidation states. Okay, so exception has chromium has plus. No, my dear, chromium is not having +1 oxidation state. No, it is copper. It is copper. I will come to those stories later. Don't worry. Sakshi, don't worry. I will discuss about this +1 oxidation state of copper. It is not chromium. Chromium cannot have +1 oxidation state. Okay. Yeah. So come to the story. Yeah. So, as I have already told you, only two elements in 3D series will have single oxidation state. One is scandium and the other one is zinc. Scandium exists in +3 and zinc will exist in +2 oxidation state. Okay, so don't forget this. These are very, very important. Oxidation topic is very, very important. Okay, and you can see some of the oxidation numbers in yellow color and some of the oxidation state in white color. So the yellow color oxidation states are the most common oxidation states. Okay, so the remaining white color oxidation numbers are also the oxidation state of that particular element, but they are like what to say? They are the unstable oxidation states. Okay, they can exist in that particular state, but in that state, it is not stable. Okay, for a long time, it cannot exist in. Suppose if you take cobalt has three oxidation states, no? So +2, +3, and +4. So among these three, only +2 and +3 are marked in yellow color and +4 is in white color. Means cobalt can exist in +4 state, but +4 is unstable. It cannot exist in +4 for long. So that is the meaning. Got it? So copper can exist in +1 and +2. So copper can exist in +1 because if it loses one of its electron, it will have 3d10 configuration. And because of that particular reason, copper can exist in +1 state. Got it? It is 3D, yeah, 3d9 configuration. 3d9, sorry, +1 means it is 3D, 3d10 and 4s1, right? Yeah, 3d10 only. 3d10 and for +2 only it is 3d9. So they can exist in both the forms. Okay, I'll tell you in which state copper will exist in +1 and in which state copper will exist in +2. So when we discuss about the standard electrode potential concepts and all, we will discuss about this copper story in detail. Got it? So scandium can exist only in one state, no, which is +3. So scandium configuration is 3d1, 4s2. So it uses all of its 3 electrons to attain this +3 configuration. And coming to zinc, which has atomic number 30. So it has 3d10 and 4s2 configuration. So zinc can lose only its 2 electrons. So zinc cannot exist in +3 state. Why it cannot exist in +3 state? Can anyone give me the answer for this? Zinc cannot exist in +3 state. Why?
Electrons are in pair.
Because of the fully filled electronic configuration. Fully filled d subshell. Okay. So third electron cannot be removed from the fully filled 3d orbital. It requires more amount of energy to take out that electron as it is fully filled, which is more stable, and that's why +3 is not possible. Okay. So because of these two configuration, D0 and D10 configuration, these two elements are having only one oxidation number. Okay. Now coming to copper. So copper can exist in +1, and also most of the elements except scandium from titanium till zinc, all elements are exhibiting this +2 oxidation state. So +2 oxidation state is the most common oxidation state for this 3D series. Got it? And then if you look into the early transition elements means from scandium till manganese. Scandium, titanium, vanadium, chromium, and manganese. So these 5 elements are called as early transition series, or early transition, or early 3D series also we can say. So these 5 elements can exist in their highest oxidation number, which will be equal to the outermost electrons in their corresponding orbitals. Okay, suppose if you take scandium, what is the electronic configuration for scandium? It is 3d1 and 4s2. So how many electrons are present in their valence shell? It is 3. So +3 is the most common oxidation state. Okay, when you come to, no, scandium will not show +2 oxidation state. Okay, so if scandium will not show +2 because there will be only one electron present if the 2 electrons from s orbitals are lost. So the 3d1 configuration is not favorable. Okay, so what it will do, instead of keeping that one electron with it, it will lose that electron also, and the scandium will try to exist in 3d0 configuration, which is more stable compared to 3d1. Got it, Jyoti? So scandium will not exist in +2, it will exist only in +3. Only +3 scandium oxidation state compounds are more stable in nature. Got it? Yes. Yeah. Then if you look into titanium, if you see to titanium configuration is 3d2, 4s2. So how many electrons are present? 4 electrons. So the outermost, the highest maximum oxidation state for titanium is +4. And when you see to vanadium, it is 3d3 and 4s2. So how many electrons are present? 5. So the maximum oxidation state for vanadium is +5. And when you go for chromium, it is 3d5 and 4s1. So there is an exception, right? So there are 6 electrons. So the highest oxidation state is +6. And for manganese, if you see, the configuration is 3d5 and 4s2. So there are 7 electrons. So it exists in +7 oxidation state. So this is applicable only till manganese. Okay, when you go for iron, it will not be applicable because for iron, the configuration is 3d6 and 4s2. So there are 8 electrons. But iron cannot have +8 configuration. You see, iron is having highest oxidation state for iron is +6 only. Got it? So this concept is applicable only for early transition series. Got it? So these are the points which you have to keep in mind. So in this lesson, mostly in all the properties, you have to keep many points in your mind. Okay. D and F block element is called as one of the inorganic chemistry lesson, right? So it is an inorganic chemistry lesson where we have to keep in mind many points. So Sakshi, why Fe did not show +1? So it is not stable in +5 oxidation state. We cannot give reason for all the things, but we can try to give the explanation. Okay, so that was the observation. If it loses, see, if iron exists in +5 configuration, so it has to lose five of its electrons, right? 2 from s orbital and 3 from d orbital. So it will have 3d, 3 and 4 is 0 kind of configuration. So this type of configuration was not observed for Fe in any of its compounds in nature. Got it? So it cannot have +5, some kind of. So these are the observations. These are the observations from the nature. So scientists have observed that and put that in the books. Okay. Fine. So now let's move on to the post-transition series. Post-transition elements means from iron till zinc. So if you take for iron, so the iron has 3d6 and 4s2 configuration. Okay, 3d6 and 4s2. So it has 8 electrons. As I have already told you, iron cannot have +8 oxidation state. Okay. So next, coming to the stable oxidation state or the oxidation state dependency. Oxidation state depends on the number of electrons which is present inside the d orbital. Okay, so there are 3 configurations which are highly stable in nature. One is D0, next is D5, and the third is D10. So if you look into the stability order for these 3, D10 is more stable compared to D5. And D5 is more stable compared to D0. And D0 is more stable than any other configuration. So that's why for scandium also I have told no. So D1 is less stable compared to D0. So that's why scandium cannot exist in +2 oxidation state. Got it? So D0 is more stable. So after that we can go for D1, D2, D3, D4, D6, D7, D8 and D9. So all these configurations are other configurations. So we have to give the first preference to D10, then to D5, then to D0. So if an element tries to attain any one of these configurations, then that compound will be more stable than the other. So based on this only, we are giving the oxidation state for most stable oxidation state for each element. Got it? So suppose if you take for titanium, so we have 2 elements, 2 ions, titanium 4 plus and titanium 3 plus. So what is the configuration for titanium 4 plus? Titanium 4 plus means it is 3d0. Titanium 3 plus means it is 3d1. So D0 is more stable compared to D1. So titanium 4 plus is more stable than titanium 3 plus. Got it? So in the same way, if I go for manganese ion, manganese 2 plus and manganese 4 plus. 2 plus means 3d5, 4 plus means 3d3. So all of you know how to remove the electrons, right? So all of you know how this 3d3 is coming from manganese 4 plus, right? So no doubt in that, no? All of you can able to take out the electronic configuration by seeing the oxidized form of that element, right? Or do you have any doubt in writing the electronic configuration by seeing the oxidized form? If you're having any doubt, just let me know now itself in the chat box. I will teach you how to take out that. Because this is very important for all the organic chemistry. Writing the electronic configuration and taking out the electronic configuration from their oxidized form. If you are having any difficulty, if any of you are having any difficulty, no doubt, yes, please. So Sakshi, you want me to teach that, like how to see the thing? Yes. Okay, I'll teach for one ion. I'll teach for the same manganese itself. Just listen to it properly. And others also who did not know how to take out this, please listen. So for manganese. So first of all, what you have to do, you have to write the electronic configuration of manganese in its neutral form. Okay, so the atomic number for manganese is 25 and the outer electronic configuration for manganese is 3d5 and 4s2. So you should be able to write this first of all. So yesterday sir have taught this, no? No doubt in writing the electronic configuration for elements, right? So all of you tell me. All of you know the atomic number and all of you can able to write the electronic configurations, right? It was discussed in yesterday's class. Yeah. So now, after writing the electronic configuration for the neutron atom, what you have to do, you have to look into the oxidation number. Okay, now manganese is existing in +4 oxidation state. So what is the meaning for this +4? 4 electrons have been lost by this manganese. So that is the meaning. So now you have to remove 4 electrons. So first you have to remove the electron from the outermost shell only. So outermost shell is 4, and the outermost orbital is 4s. So first you have to remove the 2 electrons from this and the remaining 2 electrons from 3d orbital. So if you remove 4 electrons from this configuration, you will have 3d 3 and 4 is 0. Right? So this is what we have written here. So manganese 2 plus means you have to remove 2 electrons. So only 2 electrons have been removed from 4s, and in 3d we will have 5. So manganese 2 plus is having 3d 5 configuration. So is this clear now, Sakshi? No doubt, right? Yeah. So we are writing the things electronic configurations like this only. Now if you compare 3d 5 and 3d 3, 3d 5 is more stable because it is half filled. So manganese 2 plus is more stable compared to manganese 4 plus. Got it? So by seeing the electronic configuration only, we are determining the stability of that particular ionic species. Okay. So oxidation state depends upon the stability like this. I hope it is clear. So no doubt, no? So any of you have any doubt from this part? Shall I move on to the next slide? Okay. Yeah, here in the periodic table, generally if you see, if I take the S block elements first, S block elements means group 1 and group 2, right? So the oxidation state exhibited by group 1 is +1 and by group 2 is +2. And in the same way for P block elements, if you take oxidation state ranges from +3 till +7. +3 is for this boron group, and +4 is for carbon group, +5 for nitrogen group, +6 for oxygen group, +7 for fluorine group. So each group will have only one oxidation state, one stable oxidation state. Okay, the same way, if you look into this thallium, lead, and bismuth, so thallium will have +1 oxidation state, bismuth will have, lead will have +2 oxidation state, and bismuth will have +3 oxidation state. So each element will have only one stable oxidation state. Okay, so I'll tell you why these three elements are having this particular oxidation state and why they are stable in these oxidation state when I discuss P block elements. Okay, so these elements belong to P block. So that time I will discuss why only the last member of each series, each group of P block is having this particular oxidation state. Okay, not in this lesson. But when you see to the D block elements exhibit variable oxidation state. So there is not only one oxidation state for one group, but each element has different oxidation state. Okay. So next we are going to discuss about the highest oxidation state exhibited by some of the elements. Okay. So those elements are manganese, ruthenium, osmium. So manganese, ruthenium, and osmium, they are stable only in their +7, +8 oxidation states. So they are existing in their highest oxidation state in these compounds. So all of you can able to find out the oxidation state by looking the compound, right? All of you can able to calculate the, so KMnO4 means, yeah. So if I have to find out the oxidation state of this manganese, I have to take that manganese as X. And for potassium, since it belongs to first group, it is +1. and each oxygen carries -2 charge. So I have 4 oxygen, so 4 into -2 is -8, which will be equal to 0. So x is equal to 8 minus 1, so x is equal to +7. So +7 is the oxidation state of manganese. Okay. The same way for RuO4, ruthenium tetroxide, keep this ruthenium as X, and 4 into -2 is -8. So x is equal to +8. The same way you have to do for osmium also. So ruthenium and osmium belongs to iron group, and manganese belongs to the manganese group number 5. Okay, of the big number. So they are existing in their higher, they are more stable in their highest oxidation state. They are more stable. These three elements are more stable in their highest oxidation state. Okay. We also have some elements which are stable in their zero oxidation state. Nickel tetracarbonyl, iron pentacarbonyl. I will show you the structure also. You see the structure. Nickel tetracarbonyl is having tetrahedral structure. This is like a tetrahedral, and iron pentacarbonyl is trigonal bipyramidal. So 3 CO will be in the trigonal plate, one will be above and the other one will be below. So trigonal bipyramidal kind of structure. So in these two elements, if you see the nickel and iron, both are having zero oxidation state. So why they are having zero oxidation state? Because this carbon monoxide ligand, which is called as carbonyl ligand, is a neutral ligand. So it carries the zero charge. So X plus 0 is equal to 0. So X is equal to 0. So nickel and iron can exist in their zero oxidation state also in these carbonyl compounds. Got it? Clear? So did you guys note down the points which I have taught you in oxidation state topic so far? So just keep an arrow, keep points and write. So you may not have the continuation like it is not like a story. Okay, you will have to mark or you have to note points from each topic. Yeah. So the next point is about the acidic character from oxidation state. Okay. If the oxidation state is more, then the ionic character of that particular compound will be very less. If the ionic character is very less, acidic character is more. So what I'm trying to say is, oxidation state is directly proportional to the acidic character. If the oxidation state of an element is very, very high, then that particular compound is more acidic in nature. I'll give you some examples so that you can understand better. So you see here, I have 3 compounds. One is MnO, the other one is MnO2, the third is Mn2O7. So in the first compound, the oxidation state of manganese is +2. And in the second compound, it is +4. And in the third compound, it is +7 because we have 2 manganese. So 2x, 7 into -2 is -14, which is equal to 0. So 2x is equal to 14. X is equal to 14 by 2 is +7. Okay. So the manganese oxidation state in third compound is +7. So you see here, as the oxidation state increases, the acidic character also increases. So which compound is more acidic? Mn2O7 compound is more acidic in nature. So oxidation state is directly proportional to the acidic character, acidity. Okay. So the one which is having the least oxidation state is basic in nature, and in between is amphoteric. So what is meant by amphoteric? The one which can act as an acid as well as a base. Got it? And also the one which is having the lowest oxidation state is more ionic in nature, because oxidation state and ionic character are inversely proportional. And the one which is having the highest oxidation state is more covalent in nature. Got it? So directly proportional to acidity, inversely proportional to ionic character. Oxidation state is directly proportional to acidity and inversely proportional to ionic character. Okay, so this is the relation which you are studying from this slide, and you have to apply this to the compound slides. So what they will do, they will give you some 4 compounds, 3 compounds like this. And they will give the compounds in order, and they will try ask you to find out the correct order of acidity. So what you can do, you can find out the oxidation state, and by seeing the oxidation state, you can find out the acidity. Because you all know that oxidation state is directly proportional to acidity. So using this relation, we can find out the correct order of acidity from the given 4 options. Got it? So you will get this type of application oriented questions only. So you need to understand the concept and you have to try to apply. Clear for all? Any doubt? Yeah, as the oxidation state increases, covalent character is also increasing, and acidic nature is also increasing. Yeah. Now let's go with the next slide. We'll see some more information about this oxidation state. Okay, let us try to take this chromium group. Chromium group consists of chromium, molybdenum, and tungsten. So what are the 3 elements? Chromium, molybdenum, tungsten. So now itself you memorize this. Chromium group members are chromium, molybdenum, and tungsten. Chromium, molybdenum, and tungsten. Very important. So the highest oxidation state exhibited by this particular group is +6. Why it is +6? So if I take chromium, the configuration is 3d5 and 4s1. So it has 6 electrons in their outermost shell. So it can lose 6 electrons which is present there, and it can exist in their +6 oxidation state. Okay. And the most stable oxidation state for molybdenum and tungsten is also +6 only. So in which compounds molybdenum and tungsten are existing in +6? In molybdenum trioxide and in tungsten trioxide, it is existing in +6. But chromium also can exist in their +6 oxidation state. But +3 oxidation state is more stable for chromium compared to +6. Which is more stable for chromium? +3 oxidation state is more stable for chromium compared to +6. So that's why it is acting as an oxidizing agent. So what is meant by oxidizing agent? Can anyone give me the definition for oxidizing agent? Oxidizing agent means, what is the definition, students? Oxidizing agent means electron acceptors. What is an oxidizing agent? Electron acceptors. Yeah, by undergoing self-reduction, they will oxidize the other elements. So suppose if chromium is existing in +6, it will gain the electrons to which it is getting reacted, and it will be converted to chromium 3+. Because chromium is stable only in +3. So it will not exist in +6, it will try to get reduced to +3. Okay, so the point which you are getting from the slide is the higher oxidation states are more stable on moving down the group. Okay, the higher members of each group will be more stable in their higher oxidation state. Okay, so write and keep in your notebook that the highest oxidation states are more stable on moving down the group. Highest oxidation state are more stable or becomes more stable, they becomes more stable on moving down the group. Higher oxidation state becomes more stable on moving down the group. So this is the very important point you have to keep in mind. The chromium is not more stable in their highest oxidation state, but molybdenum and tungsten are more stable. Okay, completed. Yes. So students, so with this slide, we are closing the story of oxidation state. So, do any of you have any doubts? Any doubt for anyone from oxidation state property? So, D block elements can exhibit variable oxidation state, and we have studied many points from each slide regarding this oxidation state. So, we are closing this oxidation state story, and the next we are moving into the standard electrode potential property. Okay, standard electrode potential property for M2 plus and M couple. M means metal, metal 2 plus and metal. Okay, 2 plus state and 0 state. So you are seeing a graph in front of you, right? So in y-axis we have electrode potential value for each element, and in x-axis we have the 3D series from titanium till zinc. Okay, and the red color points are the observed value, and the green color diamond shaped points are the calculated value. Okay, and copper you see in this graph, copper is having the positive standard electrode potential value, whereas other elements are having only the negative value. Only copper is having the positive electrode potential value. Okay, why? So copper 2 plus, when it gains 2 electrons, it will be converted to copper. And copper, if it reacts with hydrochloric acid, there is no reaction. No reaction occurs if the copper is treated with an acid. But if you take other elements of this series, like from titanium till nickel and zinc, they will react with HCl, HBr kind of acids, and they will give out hydrogen gas, and they will result in the formation of salt, MX type of salt. Okay, suppose if I take, what I take, let me take nickel. So 2 moles of nickel can react with the 2 HCl molecule to give 2 Ni. It is not 2 Ni, it is nickel chloride, NaCl2, 2 NaCl2 kind of salt, and hydrogen gas will be evolved. So all other metal atoms will react with acid, and they will evolve out this hydrogen, except copper. Why? Copper is having the positive value for this electrode potential. So if an element is having the positive value for this electrode potential value, then that particular element will not react with an acid. It will not react with an acid, and hydrogen gas cannot be evolved out. So the elements which are having the negative electrode potential value, they are called as reducing agents. Okay, and the one which is having positive value, they are called as oxidizing agent. So copper cannot react with HCl, but copper will react with H2SO4, and copper will react with HNO3. So HCl is the hydrochloric acid, H2SO4 is sulfuric acid, and HNO3 is nitric acid. So copper will not react only with hydrochloric acid, but it will react with sulfuric acid and nitric acid. Okay, so these are the exceptions. So it does not react only with HCl, but with the other 2 mineral acids, it will react. Got it? So take a note of that. Then coming to this tabular column. So in this tabular column, you can see that on across the period from titanium till zinc, the E0 value, the electrode potential value, which is present given in the last column, it is moving towards the 0, right? Moving towards the positive, more or less, from -1 to 0. Okay, and we have some exceptions for manganese, for nickel, and for zinc. Okay, so take for manganese. So manganese is having 1509 as a value for delta H21. So what is delta H? First of all, it is the enthalpy. It is the change in enthalpy. Means ionization energy. It is the ionization second. If I remove the second electron from manganese, then the energy accompanied with it is 1509. Okay. So because if I remove the second electron, manganese will exist in +2 oxidation state. So if manganese is in +2 oxidation state, then the configuration is 3d5. So manganese will have 3d5 and 4s2 configuration. If it loses these two electrons and if it tries to exist in +2, it will have only 3d5, which is more stable. So by losing 2 electrons, manganese is becoming more stable. So because of that, it is having the least value of the ionization energy compared to chromium and iron. So you see to the chromium is having 1592 and manganese is having lesser than that, but iron is having more value, higher value compared to manganese. Actually, the value should increase. Okay, but for chromium till manganese, it is decreasing and then it is increasing. So there is some irregularity. So you see here from chromium till manganese, it is decreasing and then it is increasing. So it should actually increase, but there is one exception because of this half-filled stable configuration of manganese. That exception is arising. Okay. Then if you talk about zinc, so see to the zinc value, zinc is having the very least value of this ionization energy. So why it is having the very least value? What is our configuration for zinc? Zinc configuration is 3d10 and 4s2. So if zinc loses 2 electrons, then 2 electrons from 4s will go, we will have 3d10. Again, 3d10 is the more stable electronic configuration for zinc. And because of that reason, very less amount of energy is required to remove those 2 electrons. So we don't have to supply more energy. Very less amount of energy is enough to remove the 2 electrons because on removing the 2 electrons, it gains the more stable configuration. Got it? So what is ionization? Basically, the energy required to remove the most loosely bonded electron in an isolated gaseous atom. So here the energy required to remove the 2 electrons from zinc is very easy. So we are supplying only very little amount of energy for zinc compared to copper. Okay. So it is related, these values are related with high negative hydration energy also. So you see for nickel, so in the hydration energy column, nickel is having the more negative. Nickel and copper, they are almost having the same value only, but nickel is having the highest value, okay, compared to the other thing. So if something is very, if the hydration energy is more negative, then that particular species is more stable. Okay, nickel is more stable in its +2 oxidation state. Nickel is more stable in its +2 oxidation state. Okay, so these are the points you have to keep in mind regarding the standard electrode potential concept. Okay, so do you have any doubts? If something is attaining the more stable configuration, then the ionization energy will be very low. Okay, manganese and zinc is having that. And if something is having the more negative hydration energy, then that particular ion is more stable. That's all. So these are the 2 points which we are learning from this particular slide. Got it? So since we are learning point by point in all the topics from this lesson, so it may look little bit dry compared to the previous lessons. So is this lesson boring for you guys? Can you all able to understand what I'm trying to say? All of you can able to understand the concepts which we are learning, no? What about others? Only Sakshi is replying. Vaishnavi, Chandana, Jyoti, Pratyusha, Ashwin, Anita. What about you guys? Can you all able to understand? So you can able to understand only if you listen the class properly. Okay, otherwise it will be boring only. Organic chemistry is very interesting basically. Only very few topics looks like this. But if you concentrate, it will be very useful and helpful for you in your examination. Okay. Good. So, shall I move on to the next slide or shall I close the today's class? What do you guys say? So shall I move on to the slide or shall I discuss the remaining thing in the next class? Does Sakshi want me to discuss the next slide? Okay, so what I'll do, I'll close, wrap it up the today's session here. So the next slide, if I start, then I have to continue for some more time. So we may not have time to complete the concept of entire topic. So what I'll do, I'll just close today's session. Sakshi, I'll continue the next slide with the next class. Is it okay? So do any of you have any doubts? Okay. Then. Thank you, students. Thank you so much. Thank you so much for listening. Sure. Take care. See you all in the next class. Bye.